this slide is perhaps the most important slide of the talk. So it's about, it explains what is the Lenski experiment. So, so we have a population of E. coli bacteria and in a glucose medium, and they reproduce asexually. They don't need to find a mate. Okay, they can reproduce by themselves. And so the most important thing is the daily cycle in Lenski experiment. So we have to understand what happens in one day, then we know what happens in every day. So in one day, we start with a certain amount of E. coli, and they reproduce asexually until there's no glucose. Okay, and they start a period of starvation. Well, this period is not important because we assume that the E. coli stay unchanged. Okay, so we don't care about this moment. Okay, so we only need to ensure that at the next certain time, they have consumed all the glucose. Okay, so the next day, or the end of the day, or the morning of the next day, they sample a certain proportion of E. coli and then put it in a fresh new glucose medium, and then it starts the same day. Okay? Every day, do the same thing in the same way, and yes, okay. So the important thing is, so it's explained in this graph, right? So this is the beginning of the day. We have a small amount of E. coli in our glucose medium, right? So there's a lot of glucose there. And at the end of the day, so the glucose has been used up, and the glucose, the E. coli has increased. The population has increased. And we sample 100, right? From, well, you can define it. Okay, so in their experiment, it's just 100. Right? So you can define whatever you want. And you sample this amount of E. coli and put it in a new glucose medium, and start the next day. Okay. Okay. Now it's working. Yes. So it's been going on since 1988, and the population has evolved, which means that the individuals, they have mutations already, new mutations, right, accumulated a long time. And they are adapted to the environment. Adapted means they are fitter to the environment, so, right? They are fitter to the environment. And the interesting thing is that the samples of the population have been stored at regular intervals, so you can consider them as fossils, right? As the fossils. The difference is that you have to look for fossils in nature. Here it's in laboratory, right? You made it, right? You made it by yourself. And we can compare the different samples and to see the difference between samples from different times, right? So we can see the evolutionary change, right? Are there any questions? Okay, so one the researchers, they are interested in relative fitness over time, right? So as we already said, that they are adapted to the environment, so it is it's not surprising that the relative fitness will increase over time, right? So they have this sketch plot, and they want to find the curves which fit this points. One is hyperbolic model, and one is power law model. This is power law model. And the hyperbolic model has what, for this one, it has unbounded limit, right? Increased to infinity. The hyperbolic, it has bounded limit. And so they are, they do know which model to choose.
How they calculate this?
Okay, I'll come back to that. How they calculate it? Okay, it's here. Sorry, I didn't explain this. Sorry. Oh, okay, I skipped one slide, right? Or I skipped this one. I skipped this one. Sorry. Yes. Yeah. Good questions. So how to define relative fitness of the strings? Consider two populations. One is unevolved string, so the population at the very beginning in 1958. Okay, I take an operation of size A naught, and another one is evolved string. I take the operation size B naught, and I put them together in the same glucose medium, and let them evolve, right? And then A naught becomes A1, B naught becomes B1, right? And what I do is B1 divided by B naught, I take a log, and divided by log A1 over A naught, right? So if you consider that the individuals, they increase exponentially, so this is the production rate of the evolved string, right? This is the production rate of unevolved string, and this is the ratio between their production rates. Okay, that's a very famous. The next sense? Okay, yeah. Yeah, so they propose two models. One is this power model, the parabola. Another is the hyperbolic model, which has upper bound. For this one, WT is as
time in days, or what you say?
Generations. So one day is one generation.
But in one day there are quite a few solutions. 10.
There are few.
If at the start of the day there were, say, 1 million cells, and at the end of the day it was 100 million, then there were quite a few divisions, because each division makes twice more. If you have a million after one division, it will be 2 millions. So it's, if one division is generation, then it is not one day.
Yes, I think you're right. I don't recall the definition of generation very clearly.
So you, okay, it's days, let's say days. Yeah.
Yeah, for me, they are not too different.
50,000 days, how many years? It's close back to 50,000. So 300 is 1 year.
I think it's days. So
maybe 3 days. No, I think it's generation. Probably it's not days.
Not days.
50,000 days. It's more than at least more than century. Century is around 30,000 days.
Okay.
So 361 year, 3,600 is 10, and 36,000 is 100 years. So okay, probably this is number of divisions.
Yeah. The real generation. Yeah. You're right. Thank you. So we want to understand why the increase of the relative phase is slow and slow. Well, it's natural, right? So on one point, it's not surprising. It increases because the individuals are fitter and fitter, right? They're more and more adapted to the environment, and it gets slower and slower. Well, they stay in a limited environment, right? It's natural to think that the increase will get slower and slower, despite the number of fixed mutations increase almost linearly. I didn't show the figure, but trust me, the accumulation of mutations is almost linear. We want to give a mathematical model to explain this curve, and especially to find out is it possible to create a mathematical model which gives the curve like that. There are many explanations for this phenomenon. Coronal interference, which means the different mutants they interact with each other, and the competition may slow down the evolution of the population. Okay, or it can be metastasis, which means the performance of a mutant will depend on the background, the genetic background. Okay, it depends on who you are with. Okay. And the last thing is the design of experiments, the daily cycles, limited supply of resources, sampling procedure, etc. So we are trying to understand if we can use the design of experiments to have a curve like that. Okay. Well, in large part of the literature, coronal interference and metastasis are considered to play a big role in this kind of phenomenon. But this study has to focus on the design of experiments to a starting point to study the Lenski experiment. So next I will talk about the individual-based modeling. So we are trying to understand the shape of the relative fitness curve. Right? So you remember the parabola. Which mechanisms are involved. And we are going to define an individual-based model, which is microscopic, for the evolution of the bacterial population, and the study of macroscopic relative fitness of the population over time. And in fact, this is a major thing in probability theory, to study the macroscopic phenomenon by using a microscopic model. So it's somehow the central topic in probability theory. For example, if we want to understand why water becomes ice at temperature zero, this is a microscopic phenomenon, right? And probabilists, they will establish a random model. So they have so we assume many individuals, particles, and we define the rules how they interact with each other. And we prove some limit theorems, and the limit theorems so under some scaling and the size of a particle goes to infinity, etc. Right? And the model is the object in the limit will have some phase transition phenomenon. So like the ice, the water becomes ice at exactly at temperature zero. Okay, so this is a phase transition phenomenon. And so we probabilists like to use the microscopic model to understand the microscopic phenomenon. And that's somehow illustrated in this model. And we have shown that in the limit of large populations on the cyclical time scale and for cyclical choice of the parameters, the relative fitness process converges, but deterministic function, a function like that one. Okay. Okay, so there are still something to say about the experiment. So we assume that every individual has a reproduction rate. Okay, so the individual will split, okay, or reproduce at the reproduction rate. It's a random phenomenon. Okay, it's a random phenomenon. It's after an exponential time, it will split. Okay, and a mutation only changes the reproduction rate. And all mutations considered are beneficial. Okay, so a type of beneficial. Why beneficial? Because non-beneficial mutations they're negligible. They cannot compete with the beneficial ones. And of course, it's also a simplification of the model. And there are two parts in the experiment. The continuous growth of a population within 1 day, and also the discrete sampling within days. Okay, in 1 day it increases continuously, and between days the sampling is discrete. Right? And at the beginning of each day, we assume there are n individuals, and within each day, individuals are produced by binary splitting at a constant rate R positive. So R is the production rate. Okay, it's a random thing, right? It's a random thing. And the reproduction process will stop when the glucose has been consumed, which happens when there are gamma times n individuals. Right? In the Lenski experiment, gamma is 1. And n individuals out of the gamma n are sampled uniformly without replacement to form the initial population at the next step. Right? So that's what we have seen at the beginning. Okay, so let's see some graphs. So at the beginning we have 5 individuals. So let's see what happens in 1 day. So they increase, continuously increase, right? So by binary splitting is increased, right? And then we reach the end of the day. There are much more individuals at the end of the day. Then what we do is sample the same amount of individuals from the end of the day, 5. Right? We sample 5 from this pool of individuals, and we don't know who will be selected. Okay, we don't know the types of the individuals. It's random, and we let it evolve again, and we repeat it since 1988. We make some assumptions. We assume that the beneficial mutations they add n to the reproduction rate of individuals that suffers mutation. Okay, so when a mutation arrives, we assume that it adds n to the reproduction rate of individuals that suffers the mutation. So this is a selected. This is a the benefit that the mutation brings to the individual. And the next is the probability that the mutation happens. And the probability is we'll call it mu n. Okay. Every individual will have a beneficial mutation with probability mu n. And this mutation affects only one. Okay, so everyone has his own mutation. Okay, affects his own. Affects his own, and every offspring of this individual will carry this mutation. Okay, so it will either spread, the mutation will either spread, or it will vanish, disappear. Okay? If this mutation um, fixate the population, which means in the end, everyone will carry the same mutation. Then it's called fixation. Right? I continuously invade the population. Right? So it means that the offspring of this particular individual continuously occupy the population. This is called fixation. And we assume that new n is much less than 0, and this will exclude the clonal interference, which means we will not, for most of the times, we will not see two different mutants coexist. Okay? What we'll see in the limit is that the mutation will either fixate or disappear, right? And only after this period, the next mutation will arrive. So we intentionally assume this to only allow one type of mutants exist. Okay, we don't see two types of the mutants coexist. We don't allow that. Well, of course, it's a simplification.
So this means that you have homogeneous population when you introduce mutation and when it becomes homogeneous again.
Yes. Yeah. Homogeneous in the sense that you only have two types, in fact. One is called the wild type, which is another is called the mutated type. Okay, wild type and mutated type. So mutated type is one mutation occurred to one wild type.
So the question is, you don't introduce any more mutations after that. So you wait when it becomes homogeneous, then you introduce next mutation.
Yes, exactly, yes. But I don't do it artificially. Okay, I prove it in a limit. Okay, I give some conditions, and I prove that we don't have two or more mutants coexist. Yeah, so
no, I'm thinking about this. You were introducing this individual-based model. So in this model, you somehow introduce mutations. This psychology is probably eventually some mutations take place here. Is that correct? So in you have described this. We even shown this trees for individual-based model.
Yeah.
So, but this would mean if we have this limit, this means we introduce mutation and wait when they all become the same, and then produce next mutation.
We don't do it artificially. So they have the right to produce, to have two types of mutants at some time. It's okay. The probabilistically is fine. What the condition that we impose here will show that, will prove that in the limit, this thing does not happen. It happens with very little.
So it's for analytics, analytical, not for individual-based model.
I think what you're saying is, in the individual-based model, you can have more than one mutation at any time. However, as time evolves, one of those mutations will disappear from the family.
Okay, so let me explain. So when a new mutation appears, it will either vanish, okay, it's equal to this, then it's down. Then another mutation appears, or it gets down, or another. So this is 0 and 1, okay, the proportion of the mutant population. Or this one is successful, it's the richest one, okay, it's the richest one. So So this is what happens in the limit. In the limit, it happens that one mutation is either vanishes or it goes to one to fix it in the population. And the next mutation only arrives when after you either vanish or you fix the population. Okay, they do not interfere. That's what happens in the limit, but when it's not in the limit, you can have two or more mutations coexist for a certain time. Okay, you can. Because it's random, right? The equation is not there. That's what we prove. So it's very technical. It's the main mathematical computation for that. Okay, so Fi is a relative fitness, and it depends on the reproduction rates of the individuals in the population. It depends on the amount of glucose you give to the two competing populations, right? And, so here comes the theorem, the first result. So let's start off with the reproduction rate at the beginning of day naught, day 0, and let's Fi the process of relative fitness. So this Fi is a random process. Okay, it's a random process, and on the assumption A, the sequence F. Okay, this is scale. So we do a time scaling. Okay, we do a time scaling. For a fixed t, so this number is large. It goes to infinity when n goes to infinity. Okay, it's very large. And this process is converged in distribution locally uniformly to the deterministic function. This. Yeah.
Why does your gamma not depend on fitness itself? Because based on the definition of fitness you gave at the start, it seems like at the end of the day you're getting more bacteria, so therefore gamma should get higher as species get.
Now the amount of glucose you give them is fixed.
Yes, fixed, but the population at the end isn't.
So we somehow also do simplification. So you have fixed initial population size. Initial population size, right? And you have the fixed amount of glucose. And then we deduce that you have a fixed fixed size at n. Okay, this is a simplification. Okay, because the amount of glucose you give them is fixed, and the initial population is fixed. Whatever their reproduction rate is, the end at end we always get the same, right? We assume that their biological activity do not consume the glucose. The glucose is only used to help them to reproduce. It's a simplification.
I get what you're saying. It just feels like that match up with your fitness definition of the relative fitness at the very start, the log B A over B naught divided by log A1 over A naught, because presumably if you've got the same population size at the start and each time your fitness is never increasing.
The relative fitness in our model, should we define it somehow differently? So okay, so if we define this T R I U Okay, let's say R in R in R is not U times N. Okay. So Ri is the reproduction rate of individual I in the evolved population, and R0 is the reproduction rate of the unevolved population. Okay, and there are n of them. And for this one, the I is from 1 to n, and the U is fixed. This is my definition of relative fitness in this model. It's a little bit different from what the biology says in their papers. Okay, so I agree there's some difference. But what I can assure you is that in the limit, they have to agree. Okay. Yeah. Okay. Okay. So, I don't know what I can do. I'm so sorry. I don't know. Yeah, I have to avoid using too much of the blackboard. Yes, but this is not quite the parabola we have seen before. The power here is 1/2, but before it's different. To create this curve, the WT, we include the epistasis. Not kind of. Okay. That's very good. Okay. So we introduce epistasis. Epistasis means the performance of the mutant will depend on the genetic record, depend on where you are, right? So where we are is, we assume the relative fitness is X, okay, the population relative fitness is X, and in this case, when mutation arrives, then it gives the beneficial, it gives the increment to the reproduction rate rho n x. This time it depends on x. X is the genetic background. Okay? And we give this form. Well, of course, it's just for mathematical convenience. I don't know what you write what that is. And in this case, we can prove that in the limit we have this curve as the limit. Well, I'm not going to give the proofs to that now. So next, I want to talk about the continuum modeling. So what's motivation? So features of individual this model is at most 1/2 mutant exist with wild type. Okay, so that's what we have explained in the level. And the reproduction rate is unknown in the long term. So this corresponds to the power law model. And the discrete generation becomes continuous time. Okay, becomes continuous time. Because after time scaling, you have the discrete generations, and after time scaling, you get continuous time. It's a mathematical thing, right? It's not. It's a bit far from the reality. So what I want to do is I want to allow different types of mutants to coexist. And the reproduction rate is bounded. Okay, it's like the hyperbolic model proposed in the biology paper. And we also assume that I also want the discrete generations to remain discrete, okay, as stay discrete. And to that purpose, I assume that we have infinite operating size and the generation that is discrete. The reproduction rate of any individual is a value in zero. Okay, this can be in any finite interval, as just for convenience. I fix it as a 0, 1. And the individuals at any generation mutate independently with probability B. Okay, this probability B is stand for dependency. Okay. And after mutation, the mutant will obtain a new reproduction rate sampled from the same mutant distribution. So what does it mean? The mutation is random, right? When the mutation arrives to an individual, you don't know what happens, right? You don't know how it comes. You don't know whether it's bad or good, right? So then we assume it's random, okay? We assume the mutant has a random reproduction rate, and how to determine this value? We give it a law, and this law is the same for all the mutants. Okay, I hope it makes sense. Now it comes the continuum model. So it's basically a dynamic system. So Pn is a distribution of the reproduction rate at generation n. Okay, this is the distribution of the reproduction rate at generation n, and the Pn plus 1 is a distribution of the reproduction rate at generation 1 plus n. And this dynamic system tells you how to update from Pn to Pn plus 1. So how do we update this? That we know that any individual will mutate with birthday P, right? Since we have a definite size of population, it means a proportion B of the population will be mutated. And once it's mutated, it will get a new value sampled from the same distribution, Q. So Q is the mutation as a mutant distribution. Okay, it is the same for all the individuals. So once it's mutated, it follows the Q distribution. So we have the term B times Q, right? For those that didn't mutate, they will go through the selection part, which means they will go to the competition part.
What is dx?
Okay. So P and dx means the proportion of the population which has fitness, has a reproduction rate x. Okay, so
It's fraction of population.
Yes. P and dx is the proportion of the population which has reproduction rate x. Okay. And so we have the selection there for those that didn't mutate.
Again, P is fraction.
P is a probability measure. Also we call it distribution.
I still don't understand what is dx. So x is the projection rate. What is dx?
Dx is like a calculus, not dx. Fx dx.
So this P should be, say, fraction of cells with x from x to x plus dx.
That's right. That's right, yes. Yes.
A bit confusing, so I can see. So I would put it like P is a function of x plus a function of x.
If you have density, you can write like fx.
So it's like
dx.
Which density function?
Yeah. If Pn has density f, then you can write it as fx times dx.
Yeah, but this, so if you would say P is a function of x and Q is a function of x, it would be somehow more or less clear.
It's a probability measure for distribution. So if it has density, you can use the density function to invert it.
And then your reproduction rate is bounded by 1. Yeah.
Yes.
On the other hand, you say that the reproduction rate in long run can grow infinitely.
Oh, well, yeah, that's, so, the biologists, they propose two models. One is hyperbolic, one is power law. Power law is the infinity, it goes to infinity, and hyperbolic is inbounded. So this one is corresponds to their hyperbolic model. They have the bounded reproduction rate in the long-term infinity. Yes. And so X is the reproduction rate, and we let the population evolve for time Tn. And since it's a reproduction rate, so it's times Te to the power Tn times X, right? And it's divided by gamma. So divided by gamma is the sampling, right? We sample from the evolved population 1 over gamma, right? And it becomes a probability measure n, right? We understand this part, right? So why I impose this thing, right? It's a response to the Lenski experiment. I let it evolve the gamma times the initial size, and then I sample 1 over gamma fraction from at the end of the day, right? So we are interested whether this model converges, and the answer is yes. The Lenski experiment has a unique linear distribution, which may or may not have condensation on the maximal reproduction rate, depending on the parameters. So here we have a phase transition effect. So we may have a condensation phenomenon happen in the limit, which means if I don't have a mass as the maximal reproduction rate, the limit may have the mass there. Okay, I maybe have some mass will travel to the maximal reproduction rate in limit, but when the time is finite, you don't have mass. So it's a phase transition depending on B. Okay, you move B, you let B bigger or smaller. This phenomenon will happen or not happen. And this model is an extension of Sir John Frank Charles Kingman. He is a very famous protein mathematician. His model is like this. Okay, he proposed it in 1978. The only difference is the selection. Okay, so in the Lenski model, we have a very clear definition. You see gamma, right? So you know what it means. And this selection, it's not very clear, right? It's a y difference, it's very simple form, and it's very nice, very nice. And I Kingman proved that it has a unique linear distribution, which may or may not have condensation depending on the parameters. And I extended it by making the D, the mutation probabilities, random. And what I impose, I assume that I represent by an RID sequence of random variables split n. Okay, so every generation, for different generations, they have different mutation probabilities, right? Before it's B for the time, right? It's B for the time. Now I make it random. I make it a little bit complicated, right? So it's called kind of Kingman model in a random environment. Right? So the environment makes the reproduction rate is random. So their question, does the PN converge? Yes. If so, when the condensation occurs, well, I have some criterion for that. It's a really complicated. What is convergence speed? So how fast it's close to the convergence limit, right? You can compute the moments of the distribution Pn, and yeah, we have some results for that. And the last question. So if we assume that the beta n, because they are RID, right? So beta 1, beta 2, beta 3, they have the same distribution, so they have the same mean, right? Assume that this RNA sequence has the same mean D, is a limit fitter in the random model than in Kingman model or overall. Fitter means you put more mass on the bigger values of X. Okay? So your mass moves more to the right towards the right, right? So that means fitter. So do you have an intuition for that one? What do you think? If I make the things random, make the probabilities random, do you think the limit will become fitter or less fitter? So what I proved is that if you make the probabilities random, the limit will be less fitter. Okay, despite that they have the same mean, right? The mean. So somehow you cultivate the reproduction probability, right? The mutation probability a little bit, right? Add some noise to the mutation probability. The consequence is that the limit will be less fitter, which means it will put more mass on the smaller values of X.
In Kingman model, it will be lower compared to this when you have random vector.
No, the random version will go lower. Okay, so yeah, so this discovery one is interesting. So maybe I should stop here.
Okay, thank you.
Thank you.
Good question.
Yes.
I don't really understand maths towards the end, if I'll be honest. But when you do the random thing, I just think it should be fixed because that's how like nature works. Things happen randomly and evolution happens. So intuitively, I would have said that would make the population just based on common.
Yeah. Well,
So have you got any comments about the relationship between kind of random mutations in nature and the results of this experiment, this numerical experiment?
which experiment? You mean the next one?
Yeah, so you're saying you've made this B thing random rather than always the same.
Uh-huh.
So you're adding noise to the system.
Yes.
And that's made the whole kind of the coli population less fit.
Well, they didn't do this experiment. In fact, they didn't do this analysis. This is my question on this metabolic model.
So is that not what, like, is the experiment in the dish attribution not based on random?
Well, in the last experiments, you never know about the reality. You cannot make an experiment based on fixed probability and another one on random probability. Because the reality is there. The real thing is there. Right? You never know if it's random or deterministic. It's just there. Only the difference is in your models. So this question is somehow unrelated to the next experiment, but I find this interesting. Okay? In the material point of view and also in the intuition point of view, right? So I asked this question to many people. And someone say it's bitter or someone says that's better. So, to make the mathematical problem interesting. So this one is not too much related to the experiment.
Mutations by definition.
Sure.
So,
No. So there are two randomness. Okay. First, individuals they mutate randomly, but maybe according to a fixed mutation probability B. Right? But now I add another layer of randomness to B. B is random. So this is so it's kind of a random environment. So different N have different environments. Okay. So in some bad environments, the B may be bigger. In some good environments, the B may be larger. So there's some noise added to B.
in amount of glucose, more glucose you say it's randomness in the environment.
Yes. Because the noise is random.
Glucose, it's in the environment. Yeah.
Yes. Well, you can theoretically argue if you need okay or not, but you never know about the random, right? I mean, it's left in the laboratory, you never know it's random environment, or maybe it's a random environment, but it does not change it for the problem and maybe related. So we don't know, it's just a mathematical.
So another point is this fitness can't go to infinity always. So we put this power law.
It can go to infinity. I mean, if you let evolve something wrong, and the ratio will go to infinity.
When cells proliferate, what they do, they take energy from glucose, they transfer it into mass of cells. Yeah. So this even so you can find limit for fitness because it will be given by total sugar you put it there. So if you put a certain amount of sugar, you can calculate, for example, up to what extra biomass it will convert. Therefore, fitness is down.
Yeah, this is physical and chemical boundaries to what we can get out of something.
So it should converge. Eventually, fitness should converge to some.
So if the recurring rate goes to infinity, it means it takes the time of co-evolution of unevolved and evolved strains will go to zero, right? And it takes less and less time to consume this common glucose if we put them together, right? So if it can happen, means the N is large and the generation is large, and one is so evolved, one is unevolved. You put them together and they consume the glucose so fast that the time limit is going to zero.
But you take samples always at certain time, therefore doesn't matter if they consume glucose too fast, it will be still same biomass at the time you take the sample. No, it doesn't matter, maybe it's not so good. Okay, more questions? Okay, thanks. Yeah.
Thank you for